For our first set of notes, we're going to look at nets and drawings for visualizing geometry. And when we talk about nets and drawings, we're talking about a net, which is taking a three-dimensional object and basically unfolding it into its two-dimensional components. Then we also have orthographic drawings and isometric drawings. And we're going to see examples of each of these as we go through this set of notes. The first thing we want to do is talk about the differences between two-dimensional and three-dimensional objects. So obviously a three-dimensional object has three dimensions, typically X, Y, and Z in three-dimensional space. If we're talking about figures, say a cube, for example, then it would have length, width, and height. So there's its three dimensions, and that's what gives it its three-dimensional properties. The other type is a two-dimensional, which would be just like if you drew a square on a sheet of paper. That would be a two-dimensional shape. It has length and width. And we're going to label these first three drawings as either two-dimensional or three-dimensional. The first drawing, we see that it has length, it has width, and it has height. So therefore, it must be three-dimensional. The second drawing has length and width, so it is going to be a two-dimensional shape. And then the third one has length, width, and height. So it's going to be a three-dimensional shape. The definition that we're going to be working with primarily today is a polygon. A polygon is going to be any two-dimensional figure that has three or more sides, and each side meets exactly two other sides at their endpoints. So another thing to consider with a polygon is that it is a closed figure, so all sides are going to meet and no sides cross one another. Examples of polygons would be triangles, rectangles, pentagons, hexagons, octagons. All of those are going to be polygons, and then there's obviously many, many more that we could draw. Using our vocabulary right now, we're going to answer 4 through 8. A polygon is formed by either 2 or 3 or more straight sides, and we know that it has to be at least 3 because the simplest polygon would be a triangle. If we only had 2 sides, we would have some kind of a V or anything like this, but it only has 2 sides, and that's not enough to create a polygon because it has this open space between the 2 sides that we're trying to draw. So a triangle is the simplest form of a polygon. It has 3 sides, and anything larger than that, 4, 5, 6, however many sides you want to draw, is going to represent a polygon. A circle, on the other hand, is not a polygon. One of the key definitions of a polygon is that it has 2 distinct endpoints. I'm going to highlight that up here at their endpoints. So a circle, we can pick a starting point. And if we go around this circle, let me change the color. We go around this circle, and we keep coming around, we're going to end right back at our starting point. So the starting point is its only endpoint on the circle. So it doesn't have the 2 endpoints required to make this a polygon. And the sides also happen to be curved rather than straight. Number 6, we have a triangle / rectangle is a polygon with 3 sides. Well, we already know that a triangle is the simplest polygon, and it only has 3 sides. Rectangles have 4, and then we can keep going on, pentagons with 5, and so on. Number 7, the sides of a polygon are straight. We mentioned that when we looked at number 5. That's one of the things. If we drew, say, a half circle, that is not a polygon. That geometric shape has this curved property, so it cannot be a polygon. Number 8, 2 or 3 sides of a polygon meet at the same point, and that's always going to be 2. If we had 3 sides meeting at the same point, that'd be this example right here, then we would end up probably creating either a 3-dimensional shape or simply just a 2-dimensional object that is not a polygon. It has to have the property that 2 sides meet at the same point. So any polygon that you draw, you'll always have this property where 2 sides meet at the same point. 9, 10, and 11, we just want to look at the figures and determine whether or not they represent polygons. Number 9 is not a polygon because of this open space between A and E. Number 10 is not a polygon because of this combined joint right here where MP and NQ intersect. So we have these sides crossing one another. And then number 11, just because it's an irregular shape, does not mean it cannot be a polygon. This one is a polygon. It's completely closed all the way around. No open spaces, no lines intersect or cross one another. All right, so here's where we get into talking about nets. As we look at our definition for a net, we're going to circle some terms that help us to create the definition. A net is going to be a two-dimensional diagram that you can fold to form a three-dimensional figure. And we'll look at it here in the notes, and then I've also created some really super fancy manipulatives of my own to kind of show how this works. 13, we want to look at circling a net that cannot be folded into a cube. Well, this first one, I have an example of that, and I'm going to go ahead and show that to you right now. Get this up here where we can see. So here is the exact same figure that you see in number 13. If I fold these two sides up and this side up, and then I fold this double square up and then over, I have now created a cube, and I hope that you guys can see this. This is kind of hard to do with a video camera, but I'm doing my best. So that first figure will fold into a cube. The second figure, on the other hand, because we have these sides joining right here, we have these four lines coming together. This cannot fold up into any kind of a cube that we would hope for. So we can circle this one because it is not a cube. The other third drawing here, if we fold this side up and this side up, and then just like we did in the previous drawing, we just keep folding these up. This side right here will actually fold over and form this opposite side. This would be our top, and this would be a side as well. So this one also will form a cube. Now, number 14 is going to be one that I'm going to use another one of my fancy created manipulatives to help us answer 14 and 15. And the way I'm going to do that is I want to label these. Instead of using colors, I'm going to label these 1, 2, 3, 4, 5, and 6. So with our fancy manipulative that I have created here, this is the exact same shape as what you see on the screen. When I fold this up, before I do that, let me show you. I have these numbered 1, 2, 3, 4, 5, and 6. So when I fold this up, you can see that we have a cube now. And on our cube, everything is numbered, but the notes have us using colors. So red corresponds to number 1. And what's opposite of number 1, right here's number 1, is here on this back side, which is number 6. So 6 would be orange. Blue corresponds to the number 3. So that's on this side. And if I rotate this around, opposite of number 3 is 5. And green corresponds to number 4. So that's this side. And when I rotate it around, opposite of number 4, I have 2, which is purple. So filling this in, we had red, which corresponded to the number 1. When we rotate that around, it's opposite of 6, so that will be orange. Blue, which is the number 3, when we rotate it around, the opposite side of it is 5, which is yellow. And then green is the number 4, and opposite of the number 4 is 2, which will be purple. And I'll number these as well, just to maybe make that easier, because if you guys print these off, maybe you don't want to print it off in color and waste a lot of precious ink. So you can also use this numbering convention that I'm using. That's 6, yellow is 5, purple is 2. And then it says, suppose you fold the net into a cube, what color is missing from each view? Using the same numbering convention and using our cube, if we orient our cube in the same fashion that we see in the notes here. So red corresponds to the number 1, so we put number 1 on top. And then we would put yellow, which is number 5, immediately down and to the right. So we're kind of looking at it this way. I hope you guys can see that. And so that means that the side that we're looking for and we're missing is 4, which would correspond to green. And then if we do the same thing with purple and blue, we put purple on top, so that's the number 2. So we put 2 on top, and then we would put 3 down and to the right. So that would be looking at it. Here's 2 on top, 3 is down and to the right. So 1 is this opposite side here. 1 corresponds to red. And then our last one, we have orange on the left, green on the right. We want to figure out what would be the top. So orange corresponds to the number 6. Green corresponds to the number 4. So if I put 6 and 4, I would have 6 to my left and 4 to my right. So that would be this figure right here. And this flat that I've got floating around here is the number 3. That would correspond to the color blue. So it may not be a bad idea to draw these out and cut them out and fold them yourselves just to get a better idea if you're having a hard time mentally picturing what I'm doing here. And 2, if you're having a hard time seeing what I'm doing, folding these up on the screen. The next problem here that shows up, I'm going to do something very similar with with the first manipulator that I showed you guys earlier. And we're given this net on the right, A, B, C, D, E, and F. And if we fold it into a cube, which letters would be on the top and the right side of the cube? So let me adjust my screen here. I'm going to try this again. So I'm going to fold this net that we have. Here's my letters A, B, C, D, E at the top, F at the bottom. When I fold this up into a cube, and I place B let's see. So there we go. I've got B like this. That's the side that's facing us, and that's what we see with that blue cube on the right of the net. It says cross out the letter of the side that will not touch some side of the face B. So every side touches the face of B except the side that's directly opposite of B. If I rotate this around, we see that it is going to correspond to side D. We can cross out side D. Number 17 says, which side of the cube will that letter be on? Circle your answer. So again, we've got B as the front. So D has to be directly opposite of that. So it's going to be on the back, away from D. And then finally, on number 18, it says, which face is to the right of face B? So here's my face B. And then to the right of that face is the letter C. And how do we know that? Well, because when we folded this, you could say, one, that it shares a side with B. You don't have to get creative with the explanation. And then the same thing, which face is on top of the cube. So again, here's B facing us. If we flip it up and look at the top, we have E. How do we know that? It shares a side with B. So we can, that can be our explanation for that one as well. All right, so let's go on. Drawing a net from a solid. So we have this three-dimensional figure here on the right, this prism, and we just want to indicate whether these statements are true or false. 20 says that 3 of the faces are rectangles. I have this face right here is a rectangle. This face right here is a rectangle. And then the bottom of this figure is also a rectangle. So 3 of the faces are in fact rectangles. That statement is true. The next question, or next statement, says that 4 of the faces are triangles. Well, I have this face is a triangle. And then I have this back one is a triangle. And that's all the faces of this that are triangles. So that is false. And then the figure has 5 faces in all. Well, we counted 2 triangles and 3 rectangles, and so that statement does have to be true because it does have 5 faces. Now write a description of the net. Again, this is not anything fancy. We just have 2 triangles and 3 rectangles fold up to form the shape. All right. And then when we look at 24, it says circle the net that represents the figure above. So let's first think about what we know. It has to have 2 triangles and it has to have 3 rectangles. If I look at the figure on the far right, this has 4 triangles, so that cannot be it. The figure in the middle has 1 rectangle and 4 triangles, so again, that can't be it. And this figure on the far left has 3 rectangles and then 2 triangles, and all the dimensions line up. So this must be our net that represents the figure that we had, that we've kind of exploded out into its 2-dimensional shape. An isometric drawing uses isometric dot paper to create the image on a 2-dimensional surface of a 3-dimensional object. So when we look at the cube structure here on the top right, first we want to count how many edges there are that are visible. And I'm just going to put tick marks through these so that we can see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There are 24 visible edges on that figure. And then we want to count how many vertices that we can see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. We have 16 visible vertices. So the isometric paper that we have here for 26 is going to allow us to draw that figure that we see above. And they've given us this first edge. And so that's going to correspond to this edge right here. And we're going to draw the rest of the shape. So if we just draw through these dots, which makes it easy to transfer the image, that's that first cube. And then we have the second cube immediately to its right. So now we've drawn the 2 base cubes. Then there'll be a cube in the back here underneath that we can't see, but we know it's there. And we're going to draw the final cube that we can see. And there we've used isometric paper to sketch out that geometric shape that we have for 25. An orthographic drawing is using the isometric drawing and imagining the 2-dimensional faces that you see depending on which direction you look at it. So if we looked at this one from the front, then we would see this square and this rectangle and then this large square. If we looked at it from the right, we would see this rectangle, this square, and this square. And that's all you could see if you looked at it directly straight on. So let me erase this first, though, because we're going to look at question 27. Underline the correct word to complete the sentence. If we built this figure here to the right out of cubes, how many would we use? So we know that this is going to be 1 cube in here, and then this is going to be a second cube, and then we'll have cube number 3 and 4 on top. So this shape right here is composed of 4 cubes. Then we have this shape right here, which is just a single cube, so there's 5. And then we have this rectangular prism in the back that is going to be 3 cubes. We have 1, 2, and then the third one is back here in the back. So that's a total of 8 cubes. Now we want to use what we know about this drawing to come up with the front, the right, or the top view of the isometric drawing. So the first one we have here is front, so I'm going to do this in black. So if we're looking at it from the front, we see this square, this large square immediately to the right, and then the 2 above it. So we have the square the large square to the right, and then the rectangle immediately above it. So this is our front view over here on the right. If we looked at it from the right, in this case, erase this, we got a lot going on right now. If we look at it from the right, we see this face, this square, and then this square above it. So we have a square, we have that first rectangular face that I indicated, and then the square above it. So this is our right view. And then finally, we're going to look at the top, and I'm going to do this one in red. If we're looking at it straight down, we have this face, this rectangular face, and this square. So we have two squares side by side and a rectangle. And that's what we see right here in this first image. And so that's going to be our top view. And the view that we see here is not existent with our particular image. So this is going to be none. That doesn't apply to any of our drawings. And then the last part of our notes here, we're going to finish up. We're going to write down first whether or not these are isometric, orthographic, a net, or none. So let's do that first. And this first image is an exploded three-dimensional shape, so that means that it is a net. There's our dogs barking. The next image we have, that goes back to our previous example here, we have the top, front, and right views, so that is going to be an orthographic. I'm just going to put ortho on here. And then our third image is the dot paper, so that is isometric. And then our last one is an actual three-dimensional object, so that is none of the drawings that we have really talked about today. And then we have a couple other labels we want to put on there. We want to write whether it's dot paper, one view, three views, or none. So the first one is one view. We only have one view of that object. The second image, we have the top, front, and right. That is three views. The third image is the isometric dot paper, so that is simply the dot paper view. And then the last one is again going to be none. So I hope that these were kind of clear. I hope that my homemade manipulatives made sense or helped you kind of visualize that a little bit. If not, let me know, and we will definitely go over this, especially that one section again together when we meet in class. But I hope everybody has a great day, and I'll be talking to you soon.